Okay, this time let's do a one-dimensional acceleration problem that actually has two stages instead of just one stage. So let's look at this problem that has a train approaching a hole in the bridge that's 1 kilometer away, and it's initially moving at 12 meters per second. And there's some heroes on the train, and after 30 seconds they finally figure out how to hit the brakes. And we want to know what acceleration they have to use to decelerate the train in time to make it stop exactly at the place of where the bridge is out. So, as with any problem, the first thing we're going to do is we're going to draw a picture. So let's prepare by drawing a picture. So let's draw an x-axis and place an origin. And we might as well place the train where it starts, initially at the origin. So let's let the initial position be at the origin. And so originally it's moving with some initial speed, call it vxi. And then after some time, the heroes decide or figure out how to turn on the brakes. And so let's mark that point as well. And let's call this by a different subscript. Let's call this vx1, the velocity at that position. And let's call that position x1. And then at some point, the train is going to come to a stop exactly at the point where the bridge is out. So the bridge should be located 1 kilometer away from where they started. So let's make that in meters. 1 times 10 to the 3 meters. And so the train stops right there, right at the location of the bridge. And since it stops, we know that its final velocity is 0 meters per second. Let's go back and label some other things in this diagram that we think we're going to need to know. Well, we know that the initial time, well, we can rather choose that initial time to be 0 seconds. And we know the initial speed at which they're moving. It tells us that they're moving at 12 meters per second. After 30 seconds, the heroes figure out how to turn on the brakes. So we can denote T1 as 30 seconds. And we don't know that position. We don't yet know what that velocity is at that point, although we can guess it pretty soon. And we also know something happens between point 1 and the final position, which is that there must be some acceleration in the left-hand direction such that the train actually slows down. Okay, so this is an example of a two-stage problem. It's two stages. There's stage 1, where the train is moving at constant velocity, and then there's stage 2, where the train is moving at constant acceleration, slowing down. So as with any problem that we solve like this, let's list the knowns and unknowns before we go into solving it in any more detail. So let's split the knowns and unknowns into stage 1 and stage 2. So for stage 1, what do we know? Well, let's list everything that we know. We know the initial x position, we know the initial x time, we know the initial x velocity, and we know, well, stage 1 is denoted by the time between xi and x1, so we know what t1 is, the time at the end of this stage. It should be 30 seconds. We also know, in fact, that there is no acceleration during this point. The train should be moving at constant velocity. So let's just explicitly say that the acceleration during this point is 0. Well, what do we not know? Well, strictly speaking, we don't know the velocity at the end of stage 1, and we don't know its position at the end of stage 1. Okay, so now let's go on to stage 2. So stage 2 is the region between point 1, namely when the people start turning on the brakes, to when the train actually stops. So what do we know about this stage 2? Well, we know T1. The initial time at the beginning of the stage is still 30 seconds. We don't really know the final time. So I'm just going to put that just since we had some initial time. We know the final velocity, 0 meters per second. We know the final position, 1 kilometer. We don't know what that initial velocity is at the beginning, so Vx1, and we don't know what the acceleration is during this period. And what we're after at the end of the day, to answer the question, is what this acceleration is. So that's what we're going to be looking for, but for now, we think we're going to need to know some of those other things as well. Okay, so to go to the next stage to solve this problem, we're going to solve it stage by stage. So the first stage that we naturally want to work with is stage 1, because stage 1 kind of feeds back into stage 2. So let's start with stage 1 in solving stage 1. So keep part of our work up there. So as we've said before, stage 1 is at constant velocity, since the acceleration is 0 in this case. And we can know something else since the acceleration is 0. We've been saying we don't know what Vx1 is, but really we do know what the velocity at the end of stage 1 is. It's the same as the velocity at the beginning because the acceleration is 0. So Vx1 is really 12 meters per second. So we can go up to Vx1, label that as 12 meters per second. And in fact, that feeds into stage 2 and lets us know that we now know that quantity as well. Okay, so what are we after? What are the other things that we don't know in stage 1? Well, we don't know what x1 is. So maybe we want to figure out what x1 is. So we're going to want to find the position at the end of stage 1. So we'll use the fact that the change in position is related to the velocity times the change in time. And strictly speaking, we should also include any acceleration. But as we said, that acceleration during this stage, during stage 1 only, is 0. So that term doesn't contribute at all. So the only contribution we have is from this first term. So the initial velocity is 12 meters per second. And the time, the change in time, well, it's the final time, 30 seconds, minus the initial time, 0 seconds. And so ultimately the change in position is 360 meters. Now this is the change in position. We don't want the change in position. Really, we want actually x1, what x1 actually is. But they're related. The change in position delta x is related to x1 because it's the final minus the initial, or rather x1 minus xi. But fortunately, since xi is 0 meters, the change in position delta x is, in this case, actually the same as x1. So ultimately, we're led to find that x1 is 360 meters. So now we've found everything that we didn't know about stage 1. And we can go on to finding what we want to find in stage 2. So in stage 2, what we'd really want to find is the acceleration. We could find the time as an intermediate step, but if we could get the acceleration in a quicker way, it'd be nicer to do that. So we're going to aim to find the acceleration. So let's do stage 2. Stage 2 is constant acceleration. And so we want to use some expression with what we know, and the one thing we don't know, the x acceleration. And one expression that will help us there is the final velocity squared is equal to the initial velocity for this stage, which is Vx1, all squared, plus 2 times the x acceleration times the change in position, the displacement during this stage. Now let's say something about this delta x, this change in position for stage 2. What this means, as usual, is the final position for this stage minus the initial position for this stage. But stage 2 actually starts at this position x1. So delta x is really xf minus x1, rather than xf minus xi. That's something to be careful about that you can get tripped up on. So it's 1 times 10 to the 3 meters minus 360 meters, so it comes out to being 640 meters for delta x for the change in position here. And this is common of all two-stage problems. You have to be careful about what you mean by delta x in these cases. Okay, so that's what we're going to mean by delta x. we want to find ax, and we know everything else in this equation. So strictly speaking, we can go ahead and solve for it. I'm going to do so algebraically, moving things around, such that ax is vxf squared minus vx1 squared all over 2 delta x. So now plugging in what we know, well, the final velocity is 0 meters per second, and the initial velocity was 12 meters per second. And now something that's easy to mess up is to forget to square those velocities up top, so be sure you do that. And then on the bottom, it's 2 times 640 meters. So I put that in my calculator, plug and chug, and see what I get. And so at the end of the day, I get negative 0.11 meters per second squared to two significant figures. The first thing you should see when you think when you see this is, hey, wait a second. That acceleration is negative. And does that make sense, or did I make a math error? Well, let's go back to our diagram up above, our original diagram, and this is why we draw it. If we look at our acceleration as we wrote it above, this does make sense. The acceleration is pointing to the left. To the left, it means a negative acceleration. So indeed, we should have expected a negative acceleration to begin with. And that's what we find at the end of the day. So indeed, this agrees with our diagram. Okay. And since this is exactly what the question was asking, we are in fact done with the problem. We wanted to find what the acceleration was in order to slow down the train so that it stops right at the point where the bridge is out, and we find that it's negative 0.11 meters per second squared, or if we were just asked for the magnitude, then it would just be 0.11 meters per second squared.